Mine.
All right, thank you. And I put the title just so that Rob would have problems pronouncing plural of amoeba. All right, so I'd like to thank the organizers of this nice conference. It's my first experience with AGNES, except for my grandmother was called AGNES. I'm so related. All right, so I'll talk about some amoebas and Berkovich spaces. So it's kind of I've been interested in general. Berkovich spaces appear a little bit from various contexts. The way I somehow got into it was through degenerations of actual complex or Archimedean data. I've been kind of doing that for a long time without actually knowing it. But here I have, anyway, some result that I think hopefully will be interesting. So it's relatively concrete to describe. Let's see where I want to start here. So. The complex torus, as you saw in June's talk, complex algebraic torus. And I'm going to look at a subvariety, so an algebraic subvariety. Okay, just cut out by a bunch of Laurent polynomials. So let me actually write this down carefully. So X is D of a bunch of polynomials. Okay, so I'm given that, and then I'm giving a map which also June was using, but in a different notation. So it's kind of a logarithm map that goes from Cn to Rn, and basically just takes the coordinates and sends them to, well, just for fun, I'm going to put a negative sign here. It's actually not so important, but you can ignore the negative signs if you want. Right, so that's a logarithm map, or kind of a tropicalization map if you want. With a more fancy language. And then the definition here is that, so this is due to Gelfand, Kapranov, and Zeleninsky. Well, I don't know when they came up with it exactly, but it's in their celebrated book. And the amoeba of X is just an image. So we call this an AX. This is the image of X under the logarithm map. So this sits inside of it. Okay. So, maybe. Okay, just as an example, why is it called amoeba? Well, because it's with some imagination, it looks like an amoeba. I think there are other examples of this in spread mathematics that are worse, actually. So, so this is a simple example. So when you have z1 plus z2 minus 1 equals 0 inside the 2 torus, right? So then you can just write in polar coordinates or something like that. You can actually explicitly write down what the amoeba looks like. So here I have, well, this is x1, this is x2, and what it's going to look like is something like something that's asymptotic to, say, x1 equal to x2. Here's, well, anyway, this is x2 equals 0, so you have these three tentacles, or whatever you want to call them. Okay? Right, so you can just completely explicitly compute that. So this has later been studied by a bunch of people. I mean, I never really worked with these myself, but I saw a lot of them because a bunch of people around me were doing it fine. So there was Mikael Pusser, fortunately passed away recently, or relatively. Let me just write a few names here. Who are, I mentioned Mikael. Alright, so why are people interested in it? Well, it's kind of, it seems like a natural object from one point of view. So let me state one result about them, which is not something I will directly use, but nevertheless. So here's kind of a remark. So there are mainly, I guess it's easier to study, just like algebraic varieties, a little bit easier to study sometimes hypersurfaces than general subvarieties. So it's true here as well. So for x inside D of f, say a hypersurface, so then you can say that the connected components of the complement, so Rn minus Ax are, so first of all, they're convex. In this case, I'll look convex, but anyway, it's something I have to prove. They're usually a bunch of unbounded ones that are related to the Newton polygon, but
do you mean x equal?
What did I say? Yeah, sorry. Yes, equal. Right. Anyway, they could be bounded. Well, maybe not in this case, but no, they could. So they could be. Anyway, they're convex, and then they're in one-to-one correspondence with convergent Laurent expansions, Laurent series expansions of 1 over n. Okay. So let me not do that in this example. I mean, I could take, this is the simplest reasonable example, but of course I could do something even simpler, right? So just do x equal to just, say, z minus 1 or something like this, right, inside. So z equal to 1 inside c star. Right? So of course that's, the amoeba is just 1 point. Right? Right. So that's the amoeba, and of course there are going to be, anyways, it's already, and of course here you could do like 1 over z minus 1, so f will be z minus 1. Of course here you can expand this as, well, minus and then 1 plus z squared or something, because there z is less than 1, and then you have another expansion here, so 1 over z minus 1, which is, I'm doing this right, otherwise I'll ask you to correct it. Okay, so I'm not really going to use that, but that's kind of one motivation for this came from the beginning. Okay, so the idea is now, if you look at a long distance, well, for some of you it is even a long distance, you'll see that this kind of looks like some kind of tripod, and those are objects that show up a lot, so these are kind of tropical objects. So let me say something about tropical notations. Certainly won't be doing kind of tropical geometry in general here. We'll just do some quick thing. Okay. So let's first do when f is equal to just a Laurent polynomial. Right. thing. Again, I mean, you can do a more or less general try to approach to talk about tropical geometry as replacing the usual operations of plus and multiplication, addition and multiplication by non-tropical versions, which would be addition and max or min, depending on your taste. Anyway, so you can, what this results here is you define kind of tropical polynomial f trop on Rn. So you just define this to be the minimum in this setting here. So it's going to be just you take alpha against x, and you take minimum all those guys for which actually C alpha is different from 0. So I don't care about what C alpha is, I just look at the ones that show up here. So this is like a piecewise, I mean this is a concave function, and it's piecewise affine. Okay? And then the V of f prop would be, well, the zero locus of this guy, except that it's not really the zero locus, but it's the locus where the set of x in Rn such that f trop is not locally affine. That is. Okay. So if I do that example here, okay, well, should I do? Well, maybe I'll do it here. So here's the same example. So here, x trop would be, well, it is what the limit should be. I mean, so f trop, so this is x trop in this case, and f trop is the function that's, if you think about it, f trop is the function that's just going to be x2 here, it's going to be x1 here, and it's 0. So f trop in this case is the minimum of x1, x2, and 0. Okay, and then so that's an example. That's kind of a definition that works well for hypersurfaces. So then the question, what do you do in general? Well, let me just give it. It's not the most satisfactory definition in some sense, but it's okay. So for x inside, say C star to the n, in general, then you just say that. So x trop just as a set. I don't care about this. I don't care about any multiplicities or so right now. So this would just be the intersection overall f that vanish over x and then d of f trop. I mean, just as a set. That's the only thing I have to consider anyway. Okay. So this is a theorem which, well, I think it's not really stated this way, but it's, you can say it goes back to, there's, I mean, some very, well, relatively speaking, old work by Bergman from '71, which is somehow pre-tropical geometry, but a lot of interesting ideas are in there. And then there's also a paper by Thierry Groves from '84. So if you kind of combine results in there, you can extract, although it's not exactly stated, you can say that the limit, if I take, I'll explain what I mean by this, but I rescale the amoeba, so this is for any x inside C star to the n. So this is the rescale limit of the amoeba is equal to x. Okay. So what do I mean by the limit here? I mean, this rescaling is just pointwise. I take for any row, I take all the points here and just multiply them by row. So then the limit, let me sweep this a little bit under the rug, but this limit, I guess you can do it either like in the Hausdorff sense, but let me actually do it in a slightly weaker sense, which kind of makes it's better for later. So this is a limit, say in the sense of Kuratowski. Okay, so let me now define what I mean by two limits. So this, I mean, what's a setting is something like this. You have x row inside some fixed topological space y, And then what does it mean? You're looking at rho mapping to X rows. You have, say, a one-dimensional family of these guys, they parameterize with real numbers, but it doesn't really matter. So I mean, what would be, to be continuous, you want to be upper semi-continuous and lower semi-continuous, right? So if I just kind of, instead of giving a definition, so something that's not upper semi-continuous, that would be that if I have a given, so this is rho, and I have a special, I want to look at a kind of special value rho naught, if somehow I have some kind of empty spots here, right? So if the nearby spaces have a lot of points that I don't see in the limit, if somehow there's some implosion, then it's not upper semi-continuous, and not lower semi-continuous would be the opposite, right? So I have, well, somehow I have a lot of stuff in this particular fiber rho naught that I don't see nearby. Okay. And I will leave as an exercise to actually formulate the definition. Okay. Let's see. Okay. All right. So now, so this again, it's not really written. So maybe a more interesting case of tropical varieties is when you have, or at least maybe beamwidth for that matter, is when you have really a one-dimensional family.
So can I,
yeah.
These convexity results don't say that if rho is less than 1, rho times the AX is contained in AX? It's not true?
I mean, I don't think that follows from the convexity itself. Right?
Is it true?
No, I don't think it's, let's see, I mean...
It's probably not true, because otherwise you can
no, I don't think it's true. I think you can have holes and stuff, right? So I think you can have holes in these guys, so... No, I don't think it's true.
How'd you get holes if you rescale?
Well, the holes disappear, right, in the limit, so... I mean, if there would be a hole in here, right, I mean, in the limit I don't see.
So you never get AGNES?
No, I mean, so this is really, I mean, I'll say, so in the one-dimensional case you get more interesting things. So these are really going to be cones, right, so that, yeah. So it's because I'm kind of using the trivial absolute value on my ground field. So to get, right, so that will be the next thing. Okay. It's always harder than it seems from people. Alright, we'll do that. Okay. So look at a slightly more general setup. So we have one parameter families. So instead I'm going to have a, well, it's also not the most general case, but we have X inside, say, C star cross C star to the N. So I have a closed subarray. And I'm assuming that the projection onto the first factor is surjective. Right. So I have something like here, I have C star to the N, and down here I have C star. And at a given value, I'm going to call this is my XA or something like that. Right. So XA is, right. This is family. So I can look at the viva of these guys. Right. So this is the, okay. And now I also want to define a tropicalization, which is kind of a standard thing, but let me, right, so this is going to be something that sits inside, not inside Rn plus 1. Okay, sorry. The amoeba doesn't lie here, sorry. The amoeba lies in Rn. And this guy is also going to lie in Rn. So this is a tropicalization. So I need to just change the definition a little bit here. Now. So how do I do the tropicalization? Let me do it in the same kind of pedestrian way. So for now, so x is equal to, first when x is equal to v of f, where I write f is equal to, so it's a Laurent series, but let me write it as first m comma alpha. So I want like cm comma alpha, and then I take first the t to the m and then z to the alpha. Right? I can do it like that, and then I associate to this an f trop of only, I only care about the z variables, so this is the minimum. Then I do like alpha comma x, but then I do plus m, and I do this for all the c m alpha. So I add the m there from t, okay, and then I define x trop in this setting. So this is still the set of x such that f trop, not locally. Fine. And then in general, I could do the same thing. So for x general, say x equals to e of, well, actually let me not do that. The problem is, so x, so I can do like that, but you have to be a little bit careful here because it's actually not trivial. I mean, or it's even not true if I take a bunch of, if x is cut out by a bunch of f1 through fm, if I only use those guys, I might get the wrong thing and I might get something too small. It's actually not obvious that it's enough to do finitely many of these guys. Okay, right. So then the theorem in this setting. So let me say, well, so in this generality. Or at least, let me see, right? Well, in this generality, it's the main thing is that I use a different point of view that people did before. So the limit, so here I want to take a limit as t tends to 0 of the amoeba, or actually, well, xt or x, if you want xa. And I want to say that this limit is equal to x prop. Except that so I have to divide by something because these are going to be, I need to rescale, and this scaling factor is something like this, 1 over log, 1 over t. Right? So I mean, if I do an example, we would see that if I have f is equal to, so say t z1 plus t inverse z2 minus 1, something like this, right? And x is equal to, or capital. Script x is v of f. And then you see that, well, the shape is the same for the tropicalization. It's just that it's not centered. I mean, this is somehow the origin lies here, I believe. Yeah, I think so. So the x trop look again like a tripod, but this. So when I rescale the amoeba, it's going to kind of look like this, but if I don't rescale it, it's going to be kind of far off in one direction. Right?
What is the denominator?
Sorry?
In the factor, what is the denominator?
So it's
minus
1 over log. Yeah, let me rewrite it. So it's 1 over log, and then it's like t inverse.
The inverse is,
Well, 1 over t, I mean, it's okay. Okay, to avoid any. Okay. I mean, it goes to 0. I mean,
okay.
This whole thing goes to 0 a little slowly. Okay, so this was done by, all right, so here is, so the case of hypersurfaces, this hypersurface case, so this is due to Mikhalkin and to independently to Brugard from, around 2000. And then, you can ask, well, isn't it trivial to reduce to the hypersurface case? It's not trivial. I would say it's possible, but it's actually quite tricky. In any case, I wanted to just present a different point of view, which kind of avoids that, and I think has some independent interest. So that's one remark. The other remark is that I formulated things inside the torus. You can do essentially at least the same proof that I'm using works for general toric varieties. So let me just mention that. And by the way, the previous results by Beery, Groves, etc., that follows if you just take your script x to be the product of your other x by C star.
There's a question.
Yeah.
Why is x prop in Rn and not Rn?
Well, you could define it as Rn plus 1, but I want it to be an Rn.
So you just
In some sense, I think of it as being defined, instead of working over C now, I really work over the Laurent series field. But it's just easier to write it this way. Okay. You have the corresponding results when instead you have x inside. Well, I guess you can make this more general too, but let's do it like this when it's inside y, where y is some toric, right? The point now. Well, so in this case, how can you find what these things are? But ax or axt and x prop. So these are going to be lying inside some y prop. So you can define some tropical space associated to a toric variety. So I guess that's been done by a bunch of people, certainly. Anyway, proving this, you have to just do things locally. It's not really more difficult, except that you define a few things. Okay, so that's kind of the results, but I think the more, so what I emphasize is that you can view this as, it's not new that a certain relation between Berkovich spaces, which I'll explain, and, tropical geometry in general. Certainly that's not at all a new idea, but I want to see this generation taken exactly as something like that. So I want to view or deduce the theorem as the kind of shadow of the corresponding result about Berkovich space. Okay, so shadow in the sense of Plato. I have to say something about Berkovich spaces.
You have two limits,
Yeah.
right? In some sense, t goes to, because C star has two missing points. So what do you get?
I'm not sure I understood the
If
question.
1 over t goes to 0 instead of t goes to
Oh yeah, you can also go in that
Yeah.
direction, and then you will do, it's just that you do, then you go to some other tropicalization. Yeah, there's another limit there. Yeah. So sure, there's nothing particular about 0 or infinity.
But there must be a relation between the two limits, no?
I think you get different, you definitely get different limits. I'm not sure if I can say anything about the relation between the two. My example, I don't think there's my example is just a shift or something like that. But, Okay, so I say something about Berkovich spaces, and then But the thing is, so Berkovich spaces are usually for non-Archimedean geometry. That's a relation to tropical varieties. But Berkovich construction originally, I mean, he made the point that in his, at least look at his book at the beginning, he really, at least in principle, generalizes how you can develop things for just general complex varieties. So I want to kind of take advantage of that. And okay. So in general, Berkovich space is kind of a way of having non-Archimedean analytic spaces analytic spaces over some non-Archimedean field. I'll just completely ignore I'll just care about the topological features. So I'll just view any Berkovich space as a topological space and ignore the structure sheet. Okay. So, and I'll also not deal with general ones. The only ones I deal with are some kind of analytifications of actual algebraic varieties. So you can do this, let's say you have an affine scheme or something like this, right? Over C. Right. So A is maybe a finitely generated C algebra if you want. Okay, so this is the setting I want to do. So I want to do slightly general. So let me here. So I want to have a norm on C. And actually, so maybe I should say that I think for the most part I will actually explain I'll say something about this second, this theorem here, but it's a little bit easier to explain when I do just the one by Bierry Groves and Bergman. I'll come to the other case a little bit later. Okay. So then I'll have a norm on C. So what kind of norm do I want? Well, of course I can have the usual norm, but let's just say in general what I want. So I want to say that it's a norm on the metric space. So for instance, something like this, and I want it to be submultiplicative, and I want it to be a norm, so it should be weight equal to 0, and I want it to be strictly bigger than 0 if A is not. Okay, so these are norms on C. Then, right, so I want to maybe, just for explicitness, the usual norm on C, I just want to have, this is the usual. Put that with an infinity here. Alright, so in this case, you can define an analytification. So this is not exactly Berkovich's. Yeah, I think it actually probably is already there, but anyway, it's certainly not my definition. That's what I'm going to say. Due to Berkovich. So I want to have bounded multiplicative seminorms. So these are going to be, so it's seminorms is a function from A to non-negative real numbers. Okay, and so what I mean by bounded are actually, that's what I want. So I want it to be bounded in the sense that it's bounded by the given norm on C, on the ground field, right? So X is spec A, right? So I want this, and then I want, well, F minus G is supposed to be less than or equal to, say F plus G. This is for F and G and A, and then I want, right? So I want this to be multiplicative. So I want this to be equal to F. Norm of F G is the product of the norms of Fg. Okay, and then you have you can put, so it's just as a set, and then what you require for topology is that you require this to be continuous for every F. This is essentially standard definition, except that usually the ground field you start as not necessarily with C, but you start with something where you actually have a multiplicative norm. So this is slightly more general. And again, I'm not going to deal with it in structure sheet, but just as a topological space. So it's going to actually have good properties. It's locally compact. Well, it's not compact, but it's locally compact. It's going to be Hausdorff. It's going to be a bunch of other properties. And you also have a tropicalization map. In this setting, so general. So this would be close again. So this is from L. So this is from Xn to Rn. And it just takes a seminorm. It's the same thing, except that now I pick and the coordinates here. Okay, sorry, I should have. Right, so now I'm assuming that X now lies inside C star to D. So I have the coordinates Z1 through Zn on A into the. So it's the same map in some sense. Okay, so so this is kind of general. So what can I get by doing this? So let me do the first example. The first example is if I just do the usual norm. Right. So in this case, it turns out that I get exactly the usual complex manifold associated to the Xn is XH or something. So this is the complex manifold associated to X. The usual identification. You just check that I give. I mean, this is you need. So of course I've written like that, but the point is if I take a point A in not A, but well, I'm not right. So X if X lies in XH, which is like a C star to the end, right? I could take the norm that to an F associates. I just evaluate F at the point X, right, and take its Archimedean norm. Right? So that gives me an embedding of X, the homomorphic, the complex manifold into the identification, and it turns out that this is all there is.
Regarding the tropicalization map, you're sending the norm to the values of minus log of that one?
Yes.
To that end, but the thing is, what's the value of that one to that end?
This is. I didn't hear the last.
What's the value of that one to that end in this case?
Oh yeah, so I mean it's the same, right? So I mean what I really do, it turns out that all these seminorms, they really come from taking a point inside C star to the end that lies on the complex manifold. And what I do is I evaluate my function at that point. So if you think about it, this is the same, it's the same map as before. So L is equal to the same as before. So of course, I mean, if I do this example, I mean again, so that's a Z1 plus Z2 minus 1 equals to 0. Well, so I should get inside C star, this is essentially a line. I mean, it's a line with 3 punctures. So I mean, you can just imagine how it looks, at least topologically, it's just I remove infinity, I remove the origin, and I remove 1. Right? So it's kind of see what that looks. Okay, so now, let me, what are the other examples of norms I can use? Let me do example, which one do I want to use? Example 0.
I think his question was, the coordinate, if you're in C star, the coordinates don't vanish at any point, but other functions can vanish, and then you take log of 0. So you need to add infinity?
No, but I mean the points here, right? So
yeah, for the coordinates it's fine, but you're defining the norm on functions.
yeah, but I mean
It's a semi.
No, but I mean, they're semi-norms, but the point is this will never be 0
For the
for
coordinates,
these guys.
yes.
Yeah.
Yes.
Yeah, otherwise okay, I mean, otherwise you would have a point that doesn't really lie on the torus. I mean, yeah, if you go through the definitions, it really will never be, this will really be a point in Rn, not in some compactification. Right, so here's example 0. And then I take the trivial norm on C. So this is just a so then I get, well, then I get an example of a Berkovich. I mean, an honest Berkovich space. Right? So this is a multiplicative norm, and well, if I do that, it turns out that the image of this under the tropicalization map, it is exactly I mean, this is not complete triviality the way I've defined it, but it's true. So it gives you really tropicalization. So I mean, if I do, again, this example, Z1 plus Z2 minus 1 equal to 0, well, so I mean, yes, so the shape, this looks like some kind of tree. It's almost the simplest possible Berkovich space. So it has a tree with one endpoint for every kind of classical point on this thing. So it's something, and I have removed, so P1 looks like a very homogeneous thing. I have everything looks the same, so I've taken, I have basically one point for every complex number, and there's one branch point. So it looks like that. Okay. Right, so that was 0 and 1. Now I can interpolate between these, so I can take example rho, or 0 between, or even equal to 0 if you want. So I'm going to take my norm to be the Archimedean norm, but to the power rho. So I'm allowed to do that, so that's still a valid norm. Okay? And in that case, it turns out that this analytification is really, I mean, it's at least homeomorphic to the usual space. I mean, it's kind of reasonable. I'm just changing things a little bit, but it doesn't really affect anything too much. So at least as an topological space, it's homeomorphic to the usual analytic space, the usual complex manifold, or complex variety, and L, but what happens is that, which is not too surprising, is that when I do L xn like this, this is really rho times the amoeba. Okay. Because of the log. So the logarithm, so this, anyway, that's where I get. Okay, so now you can kind of see that, well, if I'm claiming that I'm putting these in a family, but I have to be able to actually do this in a reasonable way. But that can be done now. So this is right, so this is really a construction due to Berkovich, which he will use for kind of quite different purposes. Right, so this will be another example when I take, what I can do is I can take as a norm, I can take the max of the Archimedean norm and the trivial. Okay. So that's not multiplicative anymore, but it is submultiplicative. So I can do everything here. And in this case, this xn is some kind of, well, what I would like to call a hybrid Berkovich space. Right? Because what I'm going to get is, I'm going to have xn is going to map to, well, it's going to map to 0, 1. So why is it 0, 1? Because that's kind of what I do just, it turns out when I do spec C, right, so I just map it to the point, and with this norm, this is 0, 1. Because what happens if I go through and just, it's an exercise, and if I look at what are the possible bounded multiplicative seminorms on the complex numbers that are bounded by this guy. Well, it turns out that it's going to be of the previous types. It's going to be, well, it's going to be example rho for rho between 0 and 1. So you have a space here that maps to 0, 1 like that. Okay? And with a the way it looks is my lambda, so here's our rho name. So here's 1, here's 0. Right, so here I have my usual guy. And here I have my branch, my tree-like thing. By the way, I should say that, I mean, so what's the tropicalization map in this case? I mean, this guy maps onto, tropicalization kind of look like that. And you see there are 3 distinguished branches, and the tropicalization map basically takes those 3 onto those 3, and everything else is just collapsed to this point here. All right, so here in between you have something rho. So there's actually it's not so important, but there's a relation. There's something you can do if you like to play around with metric spaces. If you have a metric space with metric D, you can hook up a new metric space by taking D to the rho for rho between 0 and 1. Those are kind of a snowflake metric. So you get some kind of fractal objects in that way. So let me pretend that I can get some fractal sphere here. Okay, don't take this too seriously. All right, so you have a space, and these could put together, and this Xn, just by the general theory, has some good properties. All right, so now, as it turns out, that what you need to prove here is that, okay, so let me kind of fit it here. So here's a theorem that implies what I need for the other theorem, and it is that this map, the map lambda from Xn to, well, 0, 1, is open. I mean, it's not the only thing you need to show, but it's open as just a set. The image of open sets are open. All right, so in this case, I mean, really what you need to prove is that it's for one of the semi-continuity statements about things, is that if I have a neighborhood of things, of something in this non-Archimedean fiber, then any small neighborhood will actually contain stuff in the Archimedean fiber. And proving that is not, well, for experts in Berkowitz spaces, it's not particularly difficult. But anyway, so that's that. And then, well, then you have to work, but once you do it, it works just the same way. It doesn't really matter if you're hypersurfers or not. It doesn't use any of that. And it also, it's okay to do this for toric, when X is embedded in a toric variety rather than the torts. Yeah?
I guess for it's open, it's continuous.
Yeah, sure. Yeah, the continuity is kind of automatic. So I mean, all this is really like the analytification of the structure map, right? So you always have these, yeah, good perfect. But it's so, yeah. Well, I want to point out the thing that doesn't just follow from general. Now, here is something to prove that is not super difficult, but it's not kind of part of the general package. Okay. So let me maybe just mention. So you can do a similar construction for one parameter families. So I think I'll just have time to do that. So you can cook up a similar thing. So what it's set up, so now I have instead, right, so X, so this was inside, right, so this was inside C star plus C star at the end, or toric right, and I have the projection onto C star. So I can do, I mean, this induces, right, so this induces the same kind of thing. I can do like X, script X and onto kind of C star, and, okay, so I just kind of play with that. This is the same analytification, so here I use the same max. I use that kind of thing. And inside here, so that kind of gives me a little bit too big space. What I can do inside here, I can set it just the locus where I'm going to have the variable t here. Right? So this is my spec of c to the plus minus 1. which is also a function up there. So I just say that, okay, I want log of t to be minus 1. Right? But t in this is the norm that defines the point in here. So this is a closed subset. Right? Let's set this to be some x star. So this is going to be mapped also to this C star or GM if you prefer this kind of row like that. We prefer GM or C. Right? And now it turns out, if I kind of go through exactly what happens here, this space here is actually, as a topological space, it's a closed unit, which not a unit is, but it's a disk inside C. Actually, when you do it, it turns out to be a closed disk of radius e to the minus 1, but that's not so important. Okay, and here you have the space. Anyway, so this is going to have the same kind of good properties, locally compact, blah, 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 has good topological properties. And what can you say about the fibers of this? So this x sharp 0, so this is the fiber over 0 in B. This turns out to be equal to, so homeomorphic to the Berkovich space when I take x and I base change it to look at Laurent series and then take its analytification where I use, so it's a Berkovich space over Laurent series with the usual non-Archimedean norm there. So somehow I have a central fiber that's over the disk. So here I have a kind of Berkovich space. And then at all the other points x, a, this is essentially homomorphic to the corresponding fiber that I had before. So somehow I have a kind of I start out with something that's a family of, take up the complex manifolds, fibered over some puncture unit disk, and I kind of fill it in, but not by putting some kind of complex space over the origin, but by putting in a Berkovich space. So this can be done. And then the same thing turns out to be true if I do that. So if I do the theorem, then that's the corresponding map of all the pies. And here's this pi. And again, that doesn't follow from general principles as far as I know. So you kind of have to prove by hand that whenever I have some, at least some good points, and the way I do it here, I take some points that are the maximal rank or something like that. You think of the evaluations, they have kind of maximal relative rank, and I approximate those by actual Archimedean ones. Anyway, I think I'll stop here. Thank you.
Any questions?
Yeah.
I'm trying to see why spec CAM is equal to 1.
Yeah, I mean, that's an exercise, right? So the exercise consists of